As it says, we are in, you can make that adjustment at the top if you'd like, Chapter 19. Chapter 19. It's electrochemistry. Do I have that on there? I do. Okay. Basically, this is a skill thing. Well, actually, everything we've done so far is a skill thing. But anyway, we're going to familiarize ourselves with the structure and/or components of electrochemical cells, batteries. We're looking at batteries and what a battery is and how it works and why it works. Okay. There's a variety of terms. You'll see I put galvanic and voltaic right next to each other there. The same device uses either of those names. So don't get your panties in a bunch if you hear me say galvanic one time and voltaic another time, because they mean exactly the same thing. Electrolytic, on the other hand, is the opposite of the first two that we just mentioned there. And then that's what the second point is. We're going to differentiate between a voltaic and an electrolytic cell, which means we're going to be looking at which direction the energy is going to be flowing and or whether it's going to be a spontaneous or a non-spontaneous process. Just for fun, because we're going to run into this again, what does the word... The word spontaneous is not the way you would probably use it in like an English class. Does anyone want to take a stab as to what they think spontaneous means? That would be the English, vocab kind of word kind of thing. Yes?
It doesn't need energy.
Oh, it does need energy. It's just going to happen without any extra. There's energy involved. It just doesn't need another stimulation to get it going. That's close. It was a good try. We are going to calculate cell EMF. Now, that's the technical term for it. You guys know it as voltage. Okay, so when you guys have a little battery with the two little prongs at the top, what do you guys call those? The little rectangular batteries with the two little prongs? Somebody just about said it. Goes in your smoke detectors? No, the D's are cylindrical. And so are C's and double A's and triple A's. This is the little rectangular one. 9-volt battery? You've never seen or heard of a 9-volt battery. Everyone else in the universe calls it a 9-volt battery. Yep. Guess why? Because it supplies 9 volts. And what do the D's supply? Good try. I think it's around 1.5. Does anyone have a D battery with them? Okay. Some people do. I don't know. Okay, what are the AAAs? I don't know what the AAAs are. See, somebody had one. All right, here we go. Anyway, we're going to determine spontaneity quantitatively. Okay, so what I mean by that is we're going to actually calculate the extent to which it is going to be a spontaneous process. However, that's an equilibrium, sorry about that. That is both an equilibrium and a thermodynamic issue, which means we can't cover that until after we've covered thermodynamics and equilibrium. And now, the AP, that next bullet point, says use of the Nernst equation to relate cell EMF to concentration. The AP is eliminated actually using that equation. Using the equation. However, in my opinion, once you learn about equilibrium, I think it's a good idea to, one, I'm going to show you the equation and how it relates. We can do it more in a qualitative sense, meaning it's going to be spontaneous, it's not going to be spontaneous. The voltage is going to increase, it's going to decrease. Even though they're not going to have you actually do a calculation, I think it's helpful to find out if something's going to increase or decrease. And then we're going to do some electrolysis calculation using Faraday's constant. These are all the skills that you're going to learn. To start all this thing off of, we have to know some basics, and that are what the components of a galvanic or voltaic cell are. This is not the good. I gave you the correct copy. All right, so here we go. I have anode there, right, with some dashes? Okay. At the anode, this is where oxidation occurs. So that's the first dash. Or in other words, if you're thinking in terms of trying to balance a reaction, that's going to be the oxidation half reaction. That's the process that occurs at the anode, the oxidation half reaction. This is where the source of electrons is. Now, why is that? What does oxidation mean? It becomes more positive by losing electrons. So again, this is the source of the electrons in an electrolytic or an electrochemical cell. If you were going to apply a sign, you would give it a negative sign. The AP is no longer asking you to do that. However, any other chemistry class you take beyond this course, they're going to ask you to do that, so I'm going to have you do that, just so you know it. Okay? Now, why would it be the negative sign? Because that's where the electrons are coming from. Doesn't that make some sense? Okay. Anyway, and then next is the cathode. I think you can probably figure all this out. The cathode is where the reduction occurs, or this is where the reduction half reaction will be occurring. And obviously, you don't have to write this down. It's not the point of the dash there, but this is where the electrons end up. Okay, and we would then label this has a positive sign because the electrons that are negatively charged are attracted to that positive side there.
So this is where the electrons go to?
Yep. Okay, the next component. And you can see all this. I think you should have one drawn at the bottom there, right? I stole that out of, I forget which book. Anyway, we have to have a pathway for the electrons to go from the anode to the cathode. And so we need some sort of way for this to transfer, and that could be like through a wire or even within a solution itself. But we'll talk about that here in a moment. So this is how a battery works. Okay, and the way we use it is we connect it to, I don't know, what do you want to connect? Your calculator. Okay, and so one end is the negative end, one end is the positive end, and one end is the source of the electrons. Those electrons go through the circuitry of your calculator and then come back into the battery.
So it doesn't go through the battery?
And then continues through the battery and back up to the top. All right. Now, we need to separate the oxidation half from the reduction half somehow or other. Okay? And in a very simple galvanic or voltaic cell, we're going to use a salt bridge or a porous barrier. That salt bridge or porous barrier is used to connect the half cells. Yeah, used to connect the half cells and allows aqueous ions to flow between the cells to maintain charge equilibrium. Now what I'm going to do, I'll say that again, but what I'm going to do is apply all this stuff to that little drawing down there. You'll notice it's kind of like a physics thing where it's got a bunch of arrows, and we're just going to put bird, 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 bird. Oh, sorry. Battery. No, we won't do that either. We'll actually label those things. Yeah, in physics, they would actually label this. Is anyone in AP Physics right now? Have you studied batteries, or will you? Okay. You're right, because it's all the, okay. Did anyone take physics last year besides? Yeah, right. Did you guys do batteries at all? Okay. So AP Physics 1 they did. Okay. All right, anyway. Once again, that last dash is allows aqueous ions to flow between cells to maintain charge equilibrium. Everything that we've done this year in Chapter 4 has set you up for this discussion that I'm about to have. Yep, to maintain charge equilibrium. All right, I'm just going to draw what's already on your paper so we can talk about it. And literally, you can just do this in 2 beakers. By the way, this little device right here is the original. Do I have an arrow pointing to that? I do. That is the original. Okay? This is the salt bridge. And I have some of these. I just don't know where they are right now. I think they actually might be up there. Is it possible that word way up there says, no, it says spectrophotometer. One of these cabinets says electrochemistry on it. This could be, and often is, a glass tube in the shape of a U. Therefore, this is the original.
YouTube.
Excellent. Very good, Grace. Okay, it's the original YouTube. There probably could have been.
But it was spelled U and then TUDD and then YouTube, or they see YouTube for the rights because people kept going to their website and looking and like emailing.
You're very probably right. Okay, so anyway, the way I'm going to draw this one, this is the standard way to draw an electrochemical cell. Now, because it's the standard way to do it, the AP doesn't want you to just automatically do it this way because that's the standard way. They're actually going to make you think a little bit, and we'll talk and see examples of how that's true. But typically, you put the anode on the left, the cathode on the right. If you're going to look on any textbook, it will always have the anode on the left, the cathode on the right. Do not fall into that trap on the AP exam. Actually think about what is occurring in the cell that is being drawn, or that you are drawing on the AP exam, because otherwise you might get trapped. Now, this is the salt bridge. Inside of the salt bridge are going to be ions. Typically, it's going to be something like a solution of potassium nitrate, sodium nitrate, sodium acetate, anything that never precipitates. Because remember, all sodium and potassium salts are always soluble. All acetate and nitrate salts are always soluble. So they're going to put something in the salt bridge that is not going to precipitate but provides both a positive and negative ion. You guys remember in biology, did you guys ever make Petri dishes or use Petri dishes? And you had the agar in there, that jelly-like stuff on the bottom in which you might grow some things? Okay. The best way to make a YouTube is to create, and I've done this before, you make up an agar solution, and then but instead of just using just pure water, what you do is you make a potassium nitrate or sodium nitrate solution to mix the agar in. And then you put it in the YouTube, let it cool, and now you have this like tube that's filled with this jelly-like material that doesn't flow away. Okay? Another way to do it is actually just use solutions and then put like copper or cotton plugs over here so that the solution doesn't go away either. But either way, something for the ions to be able to migrate through. Okay? All right. Now, since we're looking at the anode here, what occurs? Well, this is where the oxidation is occurring. And then obviously over here at the cathode, we're going to have reduction. Now, I'm not usually, as you guys know, a big person for mnemonic devices to help you remember things, but enough people confuse this that I'm going to give you a little hint. You don't have to use what I'm about to tell you, but I think most people find it useful. Notice that oxidation starts with a vowel, and the word anode starts with a vowel. Notice that the word reduction starts with a consonant, and the word cathode starts with a consonant. That might be helpful for you to remember which is which. Okay, so now, since, and then we need a path for the electrons to flow. So typically, they're going to be two different metals. So I'm going to put a metal over here, a strip of metal here, a strip of metal over here. In general, each of those strips is called an electrode. However, one of them is called the anode, and the other one is called the cathode. But in general, they're each called electrodes. And anyway, to connect them, we're going to put a little piece of wire. Now, the cathode could be a number of different things other than a metal. The anodes are typically metals. Different types of metals, we'll find out why it matters what metal you have. We'll find that out here very, very shortly. The cathode can be a metal, but can also be other things. It could be a metal. It could be well, platinum is a metal, but it could be graphite. Or it could be hydrogen gas, believe it or not, and we'll see that. I'm going to go ahead and put platinum in up here. Even though we know platinum is a metal, I think we know platinum is a metal. Sometimes you'll see why here in a little bit, but why specifically platinum. All right, let me see, what else do I do? Okay, so because of this, the way I've got this drawn, this is the anode. Remember, the anode is the source of electrons. So which direction, the way this is currently drawn up here, are the electrons going to flow? Clockwise or counterclockwise? Clockwise. The way this is drawn, the electrons are going to flow in this direction. Okay. Now, I think I had like a little device drawn up here, right? Mm-hmm. Or at least like a little box or something. Okay. If, listen carefully here, if this is a voltaic or galvanic cell, that's just going to be a voltmeter to measure the potential difference between the two electrodes. If it's a galvanic cell or a voltaic cell, that's going to be a voltmeter to measure, or some sort of device. Okay? It could be the thing you're actually trying to run, your cell phone, your calculator, your flashlight, whatever it happens to be. Okay? That's what could be there. If this were an electrolytic cell, it would be the source of electrons. But we're not that far yet. Anyone have rechargeable batteries? Everybody raise your hand. Where are your rechargeable batteries? Well, both your cell phones and probably your calculators, right? Okay. So what happens is during the day, that battery acts as a voltaic or galvanic cell and continually is producing electrons. But when you plug that in to recharge it, now it becomes an electrolytic cell, and things get recharged. So you're putting you're adding a source of electrons to that system to put them back into the system. Okay. Let me see. I think there's one or two more things I want to do here. Oh, and now, if the electrons are going this way, what's going to ultimately happen to the charge over here? So they can become positively charged, whereas this side is going to become negatively charged. And the battery's not going to work because there's no way for that equilibrium to be achieved. You can't force them over there without this has to maintain its charge, this side has to maintain its charge. This is the whole point for the salt bridge. Now remember, there's a salt in there. Let's just call it potassium. It doesn't matter what we call it. What's going to have to flow in this direction to maintain the charge? Cations or anions? Remember, negative charges are leaving. To maintain charge, anions are going to have to flow in this direction. So, I'll just put nitrate ion up here as an example because I've been saying potassium nitrate or sodium nitrate. Okay? And then obviously, this side's becoming more negatively charged, so what has to flow in this direction? That would be the cations. And let's just call it potassium as an example. This way the charge maintains or stays balanced on each half reaction. How are we doing so far? It's a terminology thing. I mean, you'll get used to it. You've never done this before. Joe, you never did this? Okay. Anyway. Make sure I got everything covered.
So there's air when it's like, I don't know if it's the liquid in there or whatever, but is that...
Oh, you know what? We'll call that... I don't know. What do you want to call that? They're just solutions. They're just solutions. If we can do this oxidation, half reaction, solution, and this obviously would be the reduction, half reaction, solution. And it doesn't have to be a solution. Has anyone ever... Okay, let me see. Anthony may have... One of the Travis girls has either done it and or seen it done. No, Joe never would have done it. Has anyone ever torn apart a battery before? Oh, Gracie has. Did you find what'd you find in there, Gracie?
Liquid.
Was it a liquid or was it a paste?
It wasn't like runny, it was just like, it wasn't like pouring water, but it was like a...
Was it paste-like?
Sure.
It flowed, but it wasn't like a liquid.
It wasn't amorphous.
Yeah, there you go. So it was a paste. Yeah, so one of these is going to be a paste, the other one's going to be a solid. But anyway, yes.
Okay, so you know like if you leave like batteries in something for so long, they like corrode or whatever, like they get all gross? What causes that?
The stuff's leaking out.
Well, like, I thought it was like if you leave the batteries in for a really long time.
Yeah, they leak out because they're dead. They're running out, so things leak out. Yeah, well, because they're acid batteries, and so it starts eating through whatever metal there is.
So the solution itself is not the anode and cathode, it's just that metal.
Okay, I do. Okay, let's do this. That's a fair question. This side over here is the anode. Everything over here is the anode, whereas over here, everything's the cathode. Or sorry about that. I'm not saying that right. This is the anode. This is the cathode. This is the area in which the oxidation is occurring with all the chemicals that are in there. If you give me just one more page, it will start making more sense.
Okay, I just want to make sure that, like, okay, I got it now.
Okay, I have a battery question. Why is it supposedly like put them like a refrigerator they
That may or may not be true.
Wait,
Snopes it.
people put batteries
I know
in
that.
their...
Snopes it. You know what I mean by that, right? She knows what I mean by that. You don't go to Snopes? You have no idea what I'm talking about. You mean I know something about the internet that you don't know? No, it's if you want to find out whether something's true or not, they not even close to Mythbusters. All right, where am I? Okay, here we go. Now, this is kind of a complicated drawing. Takes up a lot of space, takes a lot of room. As scientists, we'd like to get the point across without having to take up so much space and drawing a bunch of pictures. Okay? So there's something called line notation, which is a shorthand way of representing a galvanic cell. So where it says line notation, it's a shorthand way of representing a galvanic cell. The AP is no longer asking you to either produce line notation or interpret line notation, but once again, I'm telling you that the next chemistry class that you take, you will. So we'll do it. Here we do. So, was it you that asked the question about which is the anode, which is the cathode? In general, you're right. Yes, this is the anode side. This is the cathode side. This is the actual anode. This electrode is called the anode. This electrode is called the cathode. But the process happens over on that side. Where I'm going with this is, I'm going to do this in blue to separate it. So you would write the anode, the actual hunk of substance that electrode is. Okay? Then you're going to draw a single line. And then you would put whatever the solution is. And we'll get into how that's going to be taken care of. So, there's the anode. After the line is whatever the solution is actually consisting of. Then you're going to draw a double line, which represents the salt bridge, porous cup, whatever. Now, you guys haven't seen this yet. Doesn't matter. After that, we'll have the next solution, in which case is the cathode is immersed in that.
Were you supposed to type this out with this one?
I'm sorry, what's that?
Can you find me here for multiple choice? Forget about that?
Maybe. I don't know. Go take care of it. I don't know how long it's been. I'm teaching. Anyway, galvanic cells produce an electric potential difference between the half cells. There's words or phrases that all mean the same thing. You guys have heard the word voltage. I think you're somewhat familiar with it. I don't think you know what it means, but you know it has something to do with batteries. Okay? And the higher the voltage, or actually it has anything to do with any electric device. The higher the voltage, well, I don't even know if you know what that means.
Does that mean more powerful, more electricity?
Is volt is a measurement of electricity?
No, it's not.
Oh, it doesn't?
We're going to get to that really soon. Amperage?
Whoa. Not a word I said, no.
Okay, well, that's the amount of electricity, but we'll get there. All right, so anyway, you've heard the word voltage. Other synonymous words are cell EMF. That's number one there, right? What does EMF stand for? Electromotive force. And then I put a little dash there because you could write, if you'd like to, synonymous with cell potential or cell voltage. Cinnamon. Cinnamon.
No, I'm just going to go with that.
Wait, synonymous?
Synonymous with cell potential or cell voltage. Who are we missing today? We're missing people.
Shelby's at camp.
Oh, that's unfortunate. Lauren is just absent, and what's her name's out there? Okay, so you'll hear me say things like electrical potential difference, cell EMF, cell electromotive force, cell potential, cell volt. I mean, all these things, all these phrases mean exactly the same thing. I wasn't at that meeting. Number 2, cell EMF is measured in volts. The unit is the volt, which is abbreviated with a capital V. As you can see, you guys have possibly seen this before. What is a volt? 1 volt equals 1 joule per coulomb. We are going to spend, from this point forward, a lot of time talking about most of the rest of the course is going to come down to Coulomb's law. Now, those of you that had me last year may remember me throwing that in your face quite a bit. Okay? We, from this point forward, are going to be spending a lot of time with Coulomb's law. Okay, so anyway, a volt is known as 1 joule per coulomb. Now, something else I need to define. I need to keep that picture up there. You'll see why here in a little bit. Electric charge. This is just kind of bonus material. It's not really bonus because we're actually going to need this. Electric charge is equivalent to 1.60 times 10 to the negative 19th coulombs per electron. So each electron has a charge of 1.6 times 10 to the negative 19th coulombs. She's good. Okay.
Okay, so coulomb is like C over E negative. Is that like?
No, that's what the charge on an electron is. Okay. All right. As it says in number 3, cells are typically set up far from equilibrium. Okay, yeah, I know you don't know what equilibrium is specifically, but I think you have a vague idea, either from previous discussions you had in your first year course or little bits and pieces that I've added this year. What does it mean for something to be in equilibrium? May not be even, but the change is going to be the same for both sides. And right now you're probably right, you're thinking equal amounts, and that's okay. We're going to find out later when we actually study it that they maintain a certain concentration. One side's decreasing at a rate that may or may not be the same as the other side's increasing, but it's a maintenance. It's a, what do you guys call it in biology? No, did you?
Yeah, we used it in I remember equilibrium as being it was adhesion or whatever. They're not always the same, but the change is
The change is constant. The change is, yes.
Our equilibrium. Yeah, I was going to say our equilibrium, we would do dilution and stuff like that. So the big amount, the little amount.
They maintain their concentrations.
Well, yeah, well, they become equal.
Oh, you're right there. I know, and that's homeostasis is the word I was looking for, by the way. Okay. Anyway, but for now we can get away with just equilibrium is maintaining a certain concentration. Okay. However, we set these cells far from equilibrium, so the further you can get your batteries from equilibrium, the longer they're going to last, is what it comes down to. Okay. Okay, so now let's start looking at a standard cell potential, which we are now, from this point forward, going to call an E cell. Now, notice it has a little superscript 0 up there. That little superscript 0 from this point forward means standard state. We're going to use standard state for almost everything we do from now on. Okay? The standard state for anything means this: a 1 molar solution if it is a solution. So if you see that little superscript 0 and it's referring to a solution, that means the concentration of the solution is going to be a 1 molar solution. If it's a gas, it's going to be gas at 1 atmosphere of pressure. And in both cases, the temperatures are going to be 25 degrees Celsius. That is the standard state for all substances. 1 molar solutions, 1 atmosphere of pressure for gases, and 25 degrees Celsius for everything. If it's anything other than those, then it's non-standard. You guys probably do not have textbooks nearby. It would be good if you did. Should be 6 back there, plus some of you still carry yours around. I understand that very little to any of this is making a lot of sense right now because we haven't spent any time with it. For the first couple of days, it's going to seem really wacky. But as time goes on, you're going to find out this really isn't that hard. You just have to get used to the terminology and the techniques. Okay, if you could turn to page 901 to start. Did you guys find it?
Yeah. Yeah, that big table.
There's a big table. That's a small table, you're going to find out. But the big one's in the back. What did I say, 901?
Yeah.
Okay, this is a table of, well, as you can see, standard electric potentials. Okay, the AP used to give these for you. They no longer do. You do not have to memorize them. You're going to be able to deduce what's going on based on other information within the problem. Okay. Anyway, at the top, as you can see, these are they are arranged in order of decreasing electric potential. Okay. Whereas fluorine, as you can see, has the highest electric potential. Okay. Whereas down at the bottom, you'll see that lithium has the lowest electric potential. Right smack dab in the middle, well, not right smack dab in the middle, but towards the middle, you'll see a bigger black box, and in that is hydrogens, yes? Notice what the electric potential of hydrogen is. 0. Hydrogen was assigned 0. You had to have a starting point. You had to have something to compare everything else to. Hydrogen was assigned the value 0. You can see in your note packet where I said something to the effect that it uses standard production, and then the second asterisk is based on the standard hydrogen potential, or She. So that's a standard hydrogen electrode. Remember I said how hydrogen can be one of the electrodes? If that's how all the rest of them were many of the rest of them were determined, is by putting the hydrogen gas as one of the electrodes, and then putting something else over here and trying to find out what electrical potential was developed from there. Okay. Anyway, you can see as you go towards the top that fluorine has the highest oxidizing. It's the best oxidizing agent. You guys have enough knowledge to help, I think, understand why that's the case. How, if you have a single fluorine atom, which remember they don't exist because fluorine is diatomic. But if you were to have a single fluorine atom, does it have a strong attraction towards an electron? Or does an electron have a strong attraction towards it? As it turns out, the strongest. Okay, because remember, fluorine has a fairly high nuclear charge. It's got 9 protons. Okay, yet it's very, very small. So those electrons can get very, very close to the nucleus, or to the atom, okay? And so that's why it's a very good oxidizing agent. It takes electrons from other things really, really well, okay? Which means it reduces very easily, okay? That's why it has the highest reduction potential. Is this making any sense to you? Whereas lithium, on the other hand, yes, lithium is also very, very small, okay? Let me finish. But lithium is larger, significantly larger than fluorine, and remember, lithium is a metal, so it has a tendency to, it has a very small nuclear charge, so it has a tendency to lose electrons. That's why it is at the very bottom. It has a weak, it doesn't have much of an attraction towards electrons. All right, we'll pick this up.